Hi, welcome to Real Learning Center. We are taking the last session of the gravitation, which we talk about basically orbital velocity and escape velocity. So we have seen universal law of gravitation of Newton, and we've analyzed the variation of acceleration due to gravity in the on the Earth's surface, the Earth on the higher levels and the deeper levels. Then we did Kepler's laws, three most important laws of Kepler. And then now we are into orbital and escape velocity. What does it mean? So how do we leave Earth? How do we leave this gravitation and go away? Okay, that is the part we are going to talk about. So now, here actually let's start with how far can we throw something? Let's say you are standing on a tower and trying to throw. So if you throw something with not so much of speed, it will fall away, fall here. If you throw with even more higher speed, it will basically go a little further, even higher speed, a little further. What happens if you actually throw with even higher speed, very high speed? So, let's say stand on the Mount Everest and start throwing. So what will happen? Yeah. Let's say I'm now going to show you here, standing on the Mount Everest and throwing. And you are throwing, let us say you throw like 5 kilometers per second. That is the speed with which you throw. Not in your hand, of course, with a machine. Okay. Then you see, it goes from the Mount Everest. It goes there and goes farther, falls there. And in the Earth being a very sphere there, it goes halfway through and fell there. So what if I actually throw even faster? Right? If I throw faster at 8 kilometers per second, then you know what happens? It goes around one round and comes back. At 8 kilometers per second, if you throw, you can get it round like this. From Mount Everest, let us say you stand and throw. At 8 kilometers per second, you can go one round and come back to you on the other side. So that happens. Even on the Mount Everest, it will be difficult, mainly because there is Earth gravitation, Earth friction, there is atmospheric friction, and atmospheric friction will slow you down. So hence it may not come back. But if you go a little higher, where atmospheric friction is very less, it will happen. It will go around. Okay. So if you throw it even at even higher speeds, then also it will go around, but it will go around in an elliptical path, not in a circular path. More than 8 kilometers per second if you throw, it will go in an elliptical path. Okay. So that is actually what we do when we send satellites. We throw it with very high speed, but we don't throw it like standing on the Mount Everest, but we actually make a rocket go up from there with it gets thrown at a very high speed. Okay. So now we talk about how far should you really throw to escape from Earth itself. Please understand this. What is the meaning of escaping from Earth? Okay. Now, whenever you actually go around in a satellite around Earth, these artificial satellites, when you are inside an artificial satellite, have you escaped Earth? No. You can't. You have not escaped Earth. So what does it mean? It means actually you are still under the gravitational pull of the Earth, and you are still having acceleration due to gravity, and you are still falling to the Earth. But it is just that whenever you try to fall into the Earth, you already have a certain velocity, you keep falling. So actually going around is nothing but falling. You kept falling, but it just didn't fall directly to the Earth, it went around. So the feel you get, see, if you are jumping from somewhere, suddenly you feel some kind of a weightlessness. And that weightlessness is because the normal force of some platform is not acting on. So that weightlessness is, you feel no weight. Okay. But when you are falling, the force of the Earth is still acting. You have acceleration due to gravity. Then the same thing that happens. If you see the astronauts floating around in a space station, they are actually feeling that they are falling. Okay, if you are jumping from somewhere and falling, and that feel is same as the feel when you are actually floating around in a space station. Okay, that is because that is same as falling. So you are still under the influence of the Earth's gravity. when you are on a satellite. And do you think you will not be under the influence of Earth's gravity when you are on the moon? That's not true. When moon is being pulled by Earth, it's very far. You have the Earth's gravity extended. So what is the meaning of escaping from Earth? That means never to return, never to go around the Earth. So it should escape and go towards infinity. Keep going. So that is called escaping from Earth. When you want to go somewhere very far and not go around the Earth, you have to escape from the Earth's gravity. Is it possible? So when you actually send something at least 11.2 kilometers per second, then it can escape and go out of the Earth's gravity. So very far. It can keep moving. And what is the meaning of escaping? It means in the process of escaping, going towards it, never completely escape. Okay? But still there is its force is so less that a lot of other gravitational force, some other forces will come into it. Okay? So that is around 11.2 kilometers per second, or even more than that. Now that is called what we call the 8 kilometers per second, for example, we call as the minimum orbital velocity. Okay. If you send anything below 8 kilometers per second, you probably cannot send it out. Minimum is that much if you are on this surface. But if you go farther, it may be different. Okay. If you go farther, its velocity may be different. So at the surface, it's different. So orbital velocity is generally calculated for every different kind of an orbit. Okay. 8 is minimum when you go from the Earth. Okay. And you get about circular orbit with that. And if it is more than 8, you actually get elliptical orbit. Here it is not constant everywhere. It changes at every point. Okay. So maximum may be more than 8. And this 11.2 is what we call escape speed. Okay. Generally, escape velocity is the word used, but it is a miss now because there is no direction. Any direction you go, we only talk about 11 point. We don't talk about direction. So it's called escape speed. Okay. It's around 11.2 kilometers per second. It's not per hour. 11.2 kilometers in a matter of a second. It has to travel 11.2 kilometers. Only then you can escape. Hope to escape from the Earth's gravitational field. Okay. Now let us look at basically calculating the orbital velocity. So this is the International Space Station. It is there in the orbit around the Earth from many years. Actually. Both Russia and US actually use this International Space Station, and they conduct lots of experiments inside. A lot of people were there, and even from India there were people who went to International Space Station. The International Space Station is going around the Earth. At what height? It's going around the Earth at a height of about 400 kilometers, 300 something, 400 kilometers. So let's look at this scenario of International Space Station going around the Earth. And we know a lot of things. We know Earth's mass. Earth's mass is around 6 into 10 power 27 kg. We know that radius of the Earth is around 6,400 kilometers, and height is about 400 kilometers. We know the value of g. From all these, what can we compute? Can we compute the velocity of this? How fast it is going around? And can we compute how much time it takes to go around? Well, let us see. Okay, let's go back to Newton for that. Okay, so Newton said acceleration due to gravitational force is equal to centripetal acceleration. Then the scenario is there. So what is the acceleration due to gravitational force? We know that it is gm by r square. And what is the centripetal force? Centripetal acceleration is given as v square by r. We just equate it and calculate for v. So v square is equal to gm by r plus h, and v is the square root of gm by r plus h. We know all the values. We can calculate v to be. We got it around 7.7 kilometers per second. Okay. If you actually go higher and higher, if the orbit is farther and farther, you can very clearly see the denominator is bigger and bigger. So farther satellites move slowly. Nearer satellites move faster. Okay. So velocity is actually proportional to the square root of the distance. And that you can very clearly see. Velocity is proportional to the square root of the inversely proportional to the square root of the distance. The distance increases, velocity decreases in the square root way. Okay, so V is 7.7. On the surface, if you come, it is around 8. That's what we talked about. So if you go 300, 400 kilometers, it came to around 7.7. If you go a little further, it is even slower. Okay. And if you calculate the number of how much time it takes, how do you calculate it? We already know that with this speed you can go 2 pi r. Okay, so you can say t is equal to 2 pi by v, 2 pi r by v, and if you substitute those things and calculate, you get about 92 minutes. In about 90 minutes, it completes one circle, and it is you actually can watch this in the night. Actually, International Space Station is so big. Okay, in the night, it is possible to spot it in the sky, and you can see that it is moving, and it's moving very fast. It takes very less time to go from one end of the sky to the other end. It finishes one full circle in 90 minutes. Yeah, that is the International Space Station that we talked about. So we can actually calculate for many different satellites what is the time. So orbital velocity and the time both can be calculated using simple Newtonian concepts. And there is actually one, when you go further and further, it takes more time. Okay. So when you go too far, like moon, it takes 28 days. So is it possible to go such a distance so that it takes just 1 day exactly? It's possible, isn't it? You can go to certain distance where it takes exactly 1 day. So what does it mean? If the Earth is there and if there is a satellite, Earth takes 1 day to go one round. Satellite also takes 1 day to go. So if a satellite is kept on, let us say, Bangalore, okay, just directly connected to Bangalore here, you look up on your zenith. So all that time the satellite will be there only, because it takes 1 day to finish. And such a orbit where it takes exactly 24 hours is called as a geosynchronous orbit. It is synchronous with the geo movement, Earth movement. So many communication satellites which are actually needed for communicating, like for example our communications like mobile phones and TV, many of these things are using satellite communication. And satellite communication actually means the satellite has to communicate to a specific geography. It can't keep moving here and there. So we use geosynchronous satellites, and that distance happens to be around 36,000 kilometers. Compared with 400 kilometers, it is 36,000 kilometers. So you can compute for 36,000 kilometers, will you get a T of 24 hours? That is a check that you can do. Okay. So now, on one last topic which we need to understand for the orbiting satellites. So orbiting satellites actually possess energy. They are going around. They possess energy. They possess kinetic energy. They possess potential energy. They are in the gravitational field, so they possess potential energy. They are moving, hence they possess kinetic energy. So sometimes you may want to know how much energy. Okay, so we say kinetic energy is very simple, half mv square. So V we know, we calculated just now. V is simply equal to V square is given by gm by r plus h. So from the previous slide we found out that it is gm by r plus h. So this is our V square. And if you substitute it, kinetic energy will simply become half gmm by r plus h. This is our kinetic energy. Okay. And what is potential energy? So potential energy calculation is a little tricky, because this mgh doesn't work here, potential energy, mainly because the acceleration due to gravity g is very different at higher heights. If you take, for example, in our room itself, if you vary some height, so that height variation is very small when compared to the radius of the Earth. Radius is like 6,400 kilometers. So you can use mgh. Whereas when you are dealing with bigger heights, you can't use mgh. Potential energy calculation has to be done based on some fundamental rules. So potential energy is defined actually as the work done in moving something from infinity to that point. Okay. So the infinity we consider it as 0, and if you are moving from infinity to some point, then you get the potential energy at that point. So you have to use and a varying force, and you have to use summing up of all these things using integration. So let's not get there, but we know the formula. The formula for the potential energy at r plus h distance is actually equal to potential energy is equal to mg into m divided by r plus h, but negative. Why is it negative? Because when you are moving from infinity to this point, you are actually not finding it difficult to. Already it is pulling, so you are not doing the work. The gravitational force is doing the work. So potential energy is actually negative. So potential energy is minus mgm divided by r plus h. Now, which one is bigger? You can say that kinetic energy is positive and hence bigger. But actually, if you look at the value of it, like just the magnitude of it, kinetic energy is actually smaller and potential energy is bigger. Yeah, magnitude. So total energy is add these two. How do you add? When you add it actually, consider the sign too when you are adding. So minus mgm by r plus h, other one is half mgm by r plus h. It will become minus half mgm by r plus h. So total energy of a satellite orbiting around is always negative. Remember this. Total energy is always negative. Okay. Now, if the total energy were to be 0 or positive, in that case, it will actually be infinite. That means it is going away from us. It is very far from us. So whenever it is bound by the gravitational force, then it is always negative. Okay. So, and also you can see potential energy, kinetic energy actually is always smaller than the magnitude of the potential energy for any orbiting satellite. Remember, for any satellite which is orbiting, kinetic energy is always less than the magnitude of the potential energy. So these are some things that you need to know when you solve problems. Okay. So this will give us an idea of the energy of a satellite. So we have completed basically universal law of gravitation, we did variations of G, Kepler laws, and finally talked about orbital and escape velocity. This orbital and escape velocity is very useful even for sending artificial satellites and sending rockets, sending exploration to Moon or Mars. Everywhere we use this in a very rigorous way. Okay, thank you.